Hi, AP Bio folks. Today is Thursday, and we are going to continue learning about organic molecules by diving into proteins, which are built of amino acids. So before we get started today, if you haven't already, take a break, pause the video, and go and finish part 2 of the pattern matching activity. There were some instructions attached on Tuesday's post, and I will attach them again today in Classroom that explain what amino acids look like and a little about their structure. And there's some questions in there to kind of answer to make sure you understand their structure. You can take some notes on those if you don't have the handout. And then go through your molecule cards and actually pull out all the ones that are amino acids and keep them handy as we talk through today so that you can kind of check and make sure that you have the correct ones labeled as amino acids. So finish that and then come back here in a couple minutes. All right, so proteins are one of the groups of biomolecules we're going to be studying, and they are what's known as a polymer. Carbohydrates and nucleic acids are also polymers. The word polymer just means that it's composed of units that repeat over and over. So it means it has smaller building blocks. Those building blocks are called monomers that are linked together in a big long chain to create a larger molecule. So before we dig deep into proteins themselves, we're going to look at the monomers of proteins. On the screen here, you have a diagram of an amino acid. And this is kind of the basic structure. You can see every amino acid, the way you can recognize it is that has kind of this backbone of a nitrogen, carbon, carbon. So that's one thing to look for. The nitrogen is attached to two hydrogens. And if you remember Tuesday, we started talking about functional groups in biomolecules. This functional group is called an amino group. And on the other side, there's a carbon that's double bonded to an oxygen and also bonded to a hydroxide, an OH. That's referred to as a carboxyl group. So every amino acid has an amino group on one side and a carboxyl group on the other. The central carbon is attached to a hydrogen, but it's also bonded to what's often just represented as an R or the R group. R is not an actual element. If you look at your periodic table, the R in this diagram stands for the part of the molecule that's different in every single amino acid. Every amino acid, that top part is the same. It's got that NCC chain with the amino group at one end and the carboxyl group on the other. So as you look through your molecule cards, every single one should have this part in common. But the R group, you will notice, is very different. It could just be a couple of atoms. It could be a whole big, huge group of atoms that extends this molecule much farther down on this diagram. So that's the part that makes each amino acid unique and different. We're going to talk first today about how these amino acids join together to build proteins, because these monomers need to link together in a big chain to create a protein. That building of polymers, linking together these monomers, is facilitated by enzymes. Like all other chemical reactions in living things, there are enzymes that help this to happen. And those enzymes are usually proteins also. I'm going to actually show you a model of a couple amino acids and show you how this process works so that you can see how these amino acids get linked together and kind of see what that process looks like. I'm going to move the camera and get that set up, and I will be right back. Okay, so what you see in front of you right now is one amino acid. So in this model building kit, the black atoms here are the carbons. The blue is the nitrogen. So here you can see we have that NCC backbone. That's kind of the central part of our amino acid. The nitrogen is attached to two hydrogens, to the yellow. So this is our amino group, this N2. And over on this end, we have our carbon double bonded to an oxygen and also attached to an oxygen-hydrogen group. So this whole piece over here is our carboxyl group. The middle carbon is attached to a hydrogen, and in this case, the R group is just represented by this orange one. Remember, in reality, this would be a whole bunch more atoms that would be built off in this direction. But this piece is different in every single amino acid. And when we look at how amino acids bond together, the R group isn't nearly as important because that bonding happens between the amino group of one amino acid and the carboxyl group of another. So here we have another amino acid, and if I move those back, you can kind of see them. So I have them oriented so it goes nitrogen, carbon, carbon, nitrogen, carbon, carbon. So you've got them lined up with the amino group and the carboxyl group next to one another. When these two bond, again, this is facilitated by an enzyme that helps this reaction to happen. And what actually happens is the amino group of this one loses a hydrogen. The carboxyl group of this one loses the hydroxide, and a bond is formed. I have to keep one of my bonds in there between those two. So let me turn that around. Between those two amino acids. So now, first, if we just look at our amino acids, you can see we still have that central chain, nitrogen, carbon, carbon, nitrogen, carbon, carbon. And so as these start bonding together, you have this continual chain down the center that goes NCC, NCC. More amino acids can be added to this to create a long chain of these. The bond that forms right here between one amino acid and the next is referred to as a peptide bond. So this right here is a peptide bond that formed when these two joined together. And remember, these bonds can be rotated, so we could turn that however we want. There we go. That looks a little prettier right there. So our peptide bond again, carbon, carbon, nitrogen, is right here between one amino acid and the next. The other part I want you to notice, these are the pieces that I removed. And if I attach that on there, these are hydrogens, and this one's an oxygen. What do we get when we attach those amino acids? What do we have left over here? This is a molecule of water, right? You've got H2O. So this process of joining monomers together, joining these amino acids together, is referred to as dehydration synthesis. Dehydration means taking away water, right? If you're dehydrated, you don't have enough water. And synthesis means putting things together to build something. So this process is known as dehydration synthesis. So I'll go through this dehydration reaction once more. Again, first, I might as well just show you this while I'm going through it. If we want to reverse this reaction, obviously we have to put these molecules back where they were, put these atoms back into our amino acids. So we have to put the water back in to separate those two amino acids. So we take our protein chain here, we break it right at that peptide bond. And then we take this apart, our OH goes back over here where it was. And this goes right back over here. So that puts us back to having two separate amino acids. So again, dehydration reactions or dehydration synthesis takes out a water. So here's our H2O. That's the dehydration part. To synthesize, to put together and build this larger molecule. So that's the synthesis part. So that's dehydration synthesis. The reverse of that, when we add the water back in to separate it, is called a hydrolysis reaction. The word hydrolysis literally means water breakage. So hydro obviously refers to water. The lysis part, if you think back, you may have heard of a lysosome. Lysosomes break down waste in a cell. The word to lyse something means to break it. So hydrolysis literally means using water to break apart the atoms in a polymer and break it back to the constituent monomers that make it up. So I'm just going to write a couple of those definitions on the screen so that you have these definitions in slightly different words. And then we will continue on talking more specifically about proteins. Okay, so once again, just to review these one more time, a dehydration reaction, remember dehydrating is taking out the water, but by removing that water, you're actually connecting the monomers together to build a polymer. This happens in proteins. It also happens in carbohydrates and in nucleic acids. The bond that's formed through a dehydration reaction has a different name depending on what kind of molecule it is. In a protein, this is called a peptide bond that forms between the amino acids. The opposite of that is a hydrolysis reaction. And so here you have a picture of that. Hydrolysis adds the water back in. There, I'll move myself over to the other side. Adds the water back in to split apart those monomers and break up that big long molecule. So the diagram on the screen right now shows hydrolysis. If you turned the arrows around and took that water out, that would be dehydration reaction. So we're going to talk about these several times through this unit, this section of the unit, as we talk about how these polymers are put together and how these are built. All right, so we're going to end today talking a little more specifically about protein. Proteins are probably the most important group of biomolecules. They at least make up the largest portion of any of these that we're going to talk about, because proteins are necessary for almost every function in living things. They do build muscles and bone, most people know that, but they also help carry out all the chemical reactions and function as enzymes in living things. They help to transport things. They help with your cell membrane functioning, both to pump things in and out of cells and to act as signaling molecules to relay signals in and out of cells. So they do many, many, many things. Because they're so important, there are a lot of them. If you take the water out of most cells, over half of what's left is made up of protein. So like I said, it's by far the most abundant of these biomolecules that we're going to talk about. Because they do so many functions, they also have a huge diverse array of structures, because the structure of the molecule determines what it's able to do and how it functions. And so the shape of a protein is really, really critical. So we're actually going to spend an entire class period tomorrow talking about how a protein goes from being just a chain of amino acids. All proteins start, as you can see here on the left, as a chain of amino acids linked together, and there are 20 different amino acids that exist that can be combined in multitudes of ways because these chains can be very, very long. This initial structure, then, when it's just a chain of amino acids, is called a polypeptide chain. That's not a functional protein yet. That's just kind of the first step in building one. After that, that chain needs to fold and coil on itself and fold up even more. And all of that folding and coiling happens because of the chemical characteristics of the amino acids that make it up. So a protein is a biologically functional molecule, which means that polypeptide chain isn't a protein yet. It needs to fold and coil up into its shape. When it's ready to do its job, then it's considered a protein. And the folding here occurs because of the order of the amino acids and the chemical properties of their R groups. That variable part of the amino acid, each one has specific chemical properties. And some of them are hydrophobic, which if you have a hydrophobic R group, you can imagine that it's going to want to kind of hide away in the middle of a protein where it's not close to water. Some are hydrophilic and want to be towards the outside. Some of them are ionic and have different charges that may either attract or repel each other. So they interact in a lot of different chemical ways to determine the final structure of what that protein is going to look like, which then determines how it can function. Like I said, tomorrow we are going to look at this in more depth. We're going to dive into all those different levels of protein structure and how they take on those unique three-dimensional shapes. So far, we have talked in this unit about nutrient cycles, some basic chemistry, and some intro to carbon chemistry. So these are the sections in the book that we've covered already. Proteins specifically are covered in section 3.5. So if you want to kind of take a minute and preview what we're going to be looking at tomorrow, that's the part of the book where we are. A couple of things to be working on. Make sure that you are caught up on that pattern matching activity. The questions and those molecules are a big part of your notes through this section of the unit, so make sure that you're doing that and keeping up with that. And you have a Mastering Biology assignment. Next week, Mastering Biology is due on Wednesday, not Tuesday, since Tuesday is a day off of school for you. And just one more reminder, there are about 15 people who still need to register for your AP Bio exam. If you are one of them, please take care of that as soon as you can. The deadline is quickly approaching. Have a great afternoon, and I will see you again tomorrow.